So that one, the meaning of linear parameter already explained before, meaning that for each increase 1 unit, for increase of 1 unit, for each every independent variable, it will give the same effect or impact on y. So it doesn't matter what is increased from what value to what value. So say increase to 1 to 2, 2 to 3, 3 to 4, for any of, for each of the independent variable, the effects or the impacts must be the same, okay, on y, the impact on y. So example of model that are not linear in parameter is one. So if let's say you put this one, I think I'll give an example before, right? So let's say you put this 2 for example, so your beta 0 2 and then beta 1 5 for example. So then you calculate when x equal to 1, what's the value of y? When x equal to 2, what's the value of y? And when x equal to 3, what's the value of y? You can see that the amount of increment is not the same. So that's why we call it not linear in parameter. You still remember this one? I think I explained in the first lecture, right? The meaning of linear parameter, what it does mean. So linear parameter means that when x increase 1 unit, doesn't matter it's increased from what value to what value, the effects of that increment in x will give the same impact on y. So this is not linear parameter because when if you calculate, if you try to do, you replace the value of x when x is 1 and then increase to 2, increase to 3, then you see that they give different amount of increment or decrement on y. Okay, so this is not linear in parameter, so it's not linear, so it does not specify the condition for it to be that can be used using the ordinary square. Okay, the ordinary square requires the parameter to be linear. So hence we need to linearize the parameters before regression analysis can be conducted. For given example, we can transform the model using logarithmic function so that we can, if you plot the information, and this equation can be rewritten using this equation. So now, for the new equation, it is linear parameter because it is this one. When log x, not x, log x increase 1, then log y will increase by beta 1. Okay, when log x, not x, except but log x increase 1, doesn't matter from what value to what value, it always gives the same effect on y, which is equal to beta 1. So if beta 1 positive, then log y will increase by beta 1 every time log x increase 1. Okay, so that's what we call linear in parameter. So this one different. This one when x increase 1, it depends on the value of x. Then that different value of impact applies to the dependent variable y. Okay, so polynomial model. So this is one of the alternative model to the linear model that we used before. Linear model is straight line. Before, I mean, okay, this is so this is the form of linear, but not really. This one is double log. Okay, so you have y equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on. That one linear model. Okay, linear because linear model. So polynomial model, many cost function and production function are curved with changing slopes. So polynomial model enables us to estimate this curve. In polynomial model, independent variable can be in form of quadratic polynomial or any higher order exponential function. Coefficient of regression are in linear form that enable regression to be estimated through ordinary methods. So basically the relationship between y and x is not linear, it's not necessarily linear, so we can use non-linear relationship between y and x, but the model itself is the parameter in linear form. Okay, coefficient of regression are still linear form, like this one. So this one, the relationship between y and x is not linear. Linear is just like straight line, so meaning that you have 2x. So x, two variable y and x, something like this. So this is linear. So you have beta 0 plus beta 1 x. So linear is like a straight line. So relationship between y and x is a linear function. But this one, for the given example, y and x, the relationship between y and x is not linear. But after you make it linear. Okay, so this one. So now you have linear relationship between log y and log x. Okay. So between log y and log x is a straight line, but between y and x it's not straight line. So again for this one, so example this one. So we can have this kind of model, so polynomial model. So we can have the power of x. Okay, so the square of x. Okay, the power 3 of x, and so on. So at a glance, independent variables appear to be highly correlated as the same variables enter more than once but in different form. So you recall that what we discussed in the first lecture about linear dependence between independent variables. If you have variable that is related, let's say you put x1 twice, then you have perfect continuity, right? But in this case you have x1, but x1 appear again. So here you have x1, but you have x1 appear again, but it's not x1 except by the square of x1. So if you have x1, then you have a problem. You have a problem of polynomiality. So linear dependent, but in this case, linear dependent means that x1 equal to other x. Okay. So this one at a glance, independent variable appear to be highly correlated because you see that it's just like we have x1 here, we have x1 here. So as the same variable enter more than once but in different form, So however, multi-collinearity. So multi-collinearity refers to a situation when we have linear dependence between independent variables. So it is, let's say you have this x equal to other x. For example, x1 equal to 2 times x2. And then you have multi-collinearity or collinearity. So later, next week we will discuss on the topic of multi-collinearity. So we need to avoid having that problem. Of course, perfect collinearity must be avoided, but serious collinearity also should be what we call it, need to fix the problem. But if there is just not that serious problem, then you can keep that one. We discuss next week. So for this particular example, so multi-collinearity may not actually exist because those variables are not linearly correlated. Okay, because if you cannot say x1 equal to how many x2, how many x1 equal to how many x1 squared. So you cannot have that equation. So you don't have the problem of collinearity. Collinearity when you can write, for example, x1 equal to how many times x the other x. Okay. But in this case x1, this one x1 squared. So you cannot. So you cannot, if you cannot, you are not able to write x1 equal to how many times this one, how many times x1 squared, how many times x1 to the power of 3, then you don't have the problem of collinearity. Okay. So for instance, in second equation, all the variables x1 squared, and x1 to the power of 3 are not linearly correlated. Okay, example that we can use, an example where we can use a polynomial function, okay, to estimate relationship between variables. So this example, production cost of sport car, say an exotic sport car company wishes to estimate its average per function. A polynomial model to estimate average per function is given by this. So this one, if you inspect the series of the variable, then you can see that the use of linear model or linear relationship between y and x is not suitable to represent the relationship between these two variables, cost and average cost. So you open the data, this one. So you have two variables. So cost is number of cars produced, and then the cost average, the average cost of producing a unit of car. So if you inspect you produce plot between the two. So let's say you want to produce scatter plot, for example, then you need to choose your x variable first, your independent variable, and then your dependent variable. So our independent variable is number of cars produced, and then is our dependent variable. So if you select this one, press Control, and then select the second so just like x and y lah. So this is our x, this is our y. So x is number of cars, and then y our average cost. So you choose this one, and then you right click, open as group. Okay, open as group, and then you go to view graph. So you open group just now. After you create a group, and then you go to view graph, and then you choose scatter plot. Scatter. Okay. So you can see this one, the relationship between average cost and cost. So definitely, the use of linear model, that is straight line, is not suitable to represent a relationship between y and x. So you have to use an alternative model. So for this one suitable model is the one that we call as quadratic regression model. So let's say what happened if you use a straight line, you estimate a model, linear model, the one we call the linear model. Okay, now this one. So you estimate model, estimate equation, quick estimate equation. So let's say so here our x, our y, dependent variable is average cost, and then your c for intercept, and then we have c for beta 0. So if you estimate linear model like this, and then you get this estimate, and you go to view actual fitted graph. So you need me to repeat, just let me know. Just raise your hand, ask me to repeat. Repeat. From which one? From which part? Scatter plot. To produce scatter plot, actually. You already produced this one. So you already produced scatter plot. Equation. Which one? Oh, this one. This go to quick estimate equation. Quick estimate equation. So you put your average cost, and then your cars in the dependent variable. So y space c space x. So let's say we just apply a linear model. So what happened? Whether it is suitable or not to be used on this to represent the relationship between y and x, between average cost and cost. So you get this estimate. This one the beta 0 lah, estimate of beta 0. This one estimate of beta 1. Okay, so you go to view. After you estimate this one, you go to view actual fitted residual graph. Okay. So you see, this is your y hat. This is the red line. The green line is your fitted value is given. So fitted value is the estimated value of y, the y hat. The estimated value of y given each value of x. So when x equal to 1, what is the value of y? Estimated of predicted value, and so on. So you see that our model, it is assumed a linear relationship between y and x, which is not suitable because it's not actual. The red one is the actual between y and x, but we apply a straight line or linear, so linear model unable to correctly fit the data. Okay, so instead of using linear model, you have to use alternative model. For this one, a more suitable model is the one that we call as quadratic one. So to estimate quadratic model, you can just use this one as given here: x and x square, x and x square. So you re-estimate model, re-estimate, so estimate again. So you have to add x square, which is cos square. So just the average cost. You can type using this one also, but I think it's faster to write like this. We just put, when you use the dependent variable followed by C for intercept, and then follow the list of independent variable instead of using this one. This one also produce the same estimate. Okay, so okay. So now you get the estimate. So now you check again. You go to view, remove actual fitted residual graph. So now you see it fits the data better than instead of straight line. It produces the y hat, the predicted value is a curved line instead of, so meaning that it's able to capture the curve instead of a straight line to represent relationship between y and x. So this quadratic model is better for this given data, okay, better to be used. It's more suitable. Alright, so this is the data itself. So this is use Excel. I think last time I already first lecture I showed you how to use Excel. So you can use the data analysis tool. You just select regression and then you can select your y variable and then your x variable. You get the same. Okay. So we can use the regression output to estimate the average cost at different weekly production level. The estimated average cost will produce average cost curve as illustrated by the following figure. Okay, so the estimated value of y for given value of number of cars produced. So that's the quadratic of polynomial. So in this case we have up to square of the x variable. Now log model. So in log model, natural logarithm is used to transform one or more variables. Log model presents non-linear relationship between independent variables and dependent variables. So I hope you understand what the difference between independent and dependent. Dependent your y, your y is dependent, your x is independent variable. So similar to polynomial model, although the relationship is non-linear, meaning that between y and x is not linear, but the coefficient enter the relation in a linear manner. Okay. So because this let me for us log, because in this case it appears as log of x and log of y. So there are two commonly used log model. There is double log as well as semi-log model. So later we discuss how to interpret different model. So double lock model. What is double lock model? A double lock model is a model which takes the natural log on the independent and dependent variables. So in the model, all variables are transformed using log information. Okay. So in Excel, you transform using an n, but if we use log give the same. The same is actually the same, represent or produce the same thing. So natural log. So except the intercept, the regression coefficient of a double log model are interpreted as elasticity. Elasticity is the percentage change in a variable following 1% change in another variable. The estimated beta 1, for example, we can here estimate the average percentage change in y for 1% change in x as 1 given the other variable remain unchanged. So linear model, before how we interpret, we see that when x increase 1 unit, then y is expected or estimated to increase or decrease by beta 1. Okay, but for double log model, we interpret not as unit, not when x increase 1 unit, then y will increase or decrease by how many units. But in this case, elasticity represents how many percent. So when x increase 1%, then y will increase or decrease by how many percent? Okay, that's why we call elasticity by percent. So the estimated beta 1, for example, this one, estimate the average percentage change in y for 1% change in x1 given the other variable remain the same or unchanged. One common application is the price elasticity or demand that is percentage change in quantity demanded for 1% change in the price of output, price of product. So elasticity can be estimated by double log model. So you can, there are a number of different ways you can use. Later I show you. The first one, the easiest one, you can produce estimate of elasticity between variables using double log model. Okay, but you also can produce or get estimate of elasticity using linear model, but you have to do some calculation. So later I'll show you. So you have to. So it is easier to use double log model as it provides direct estimate. No need to calculate. You can just take the estimate of the slope. Okay, the estimated slope gives us the estimated elasticity between variable. So elasticity can be estimated by double log model. Double log models are suitable when independent and dependent variables are related with constant elasticity and not constant slope. Example, estimate the price of elasticity for demand of coffee. So consider data on number of cups of coffee consumed daily by an individual and the price of coffee per pound as given by the following table. So we have the data, the annual data on the consumption of coffee, number of cups per person per day. So average lah, this one. And then X is the price. So we want to estimate. So you have data. So you want to estimate the elasticity between the demand and price. So when price increase $1, for example, sorry. So in this case we interpret a percent. So when the price increase 1%, not 1 unit. If you want to estimate in terms of unit, when the price increase 1 unit, how much consumption of cup affected increase or decrease? That one you just use linear model like before. You just replace y against x. You just replace y against x. That's how you interpret it. Okay. So for example, you have this data. So we have coffee data, this one. So if you just simply regress as usual, meaning that you estimate linear model. So you go to quick estimate equation, just like before. If you simply, so this is data of the demand of coffee in cups. How many cups of coffee, and then this one, the X is the price. So if you estimate just like before, y space c space x, So this example, so this one you have to be careful when you use this model, how to interpret. When you use double log model, how to interpret, because the way that we interpret the estimated coefficient is different. So if you just regress y against x, how to interpret? So we say that when x, the price increase $1, because the data is pound, so £1. So when the price increase by £1, then the consumption will reduce by 0. Because it negative reduce, reduce by 0.4795 cups. That's how we interpret for using, if you use linear model. But now if we are interested to estimate elasticity, so we want to know how many percent. Let's say if the price increase 1%, what happened to the demand? And that's elasticity. So we can use alternative model, the one we call as double log model. So a suitable double log model to estimate price elasticity or demand for coffee is given by this log y, and then we have independent variable log x. So many economic textbooks illustrate demand curve are as linear, hence constant slope. However, the elasticity changes along the demand curve. The demand curve are not necessarily linear. The above double log model depicts a non-linear demand curve with constant elasticity. So if to estimate the elasticity, instead of using this one, or maybe you can save this one. If you want to save you just click this one, close, and then you say name as equation 1. Okay. You can put whatever name. So this one, the default one is equation 1. You can change if you want to put different names up to you. Now we want to estimate elasticity, because this one in terms of interpretation, we interpret as unit. When x increase 1 unit or $1, what happened? How many units are demand increase or decrease? Okay, but now we want to estimate elasticity, so we use double log model. So again, so in Excel, to transform variable to be in natural logarithm, you just use n. But in Windows, you use log. So we have y, the demand, and then we have x. Okay. So this is your estimate using double log model. So this is what we call double log model. Double log model when we transform all variable using log transformation. So all variable y as well as all x, then that's what we call double log model. So this just give us an estimate of elasticity. So why we are able to estimate as percent? This one. So I give you in spectrum, I provide this. If let's say you are using linear model between y and x, so the slope represent the changes in y per changes in x. Okay. So that's how we interpret as usual. We say that when x increase, when you estimate, you get estimated slope, you say that when x increase 1 unit, then y will increase by beta 1. Okay. But if you use double log model, so this one it has error term, so I forgot to put this one. Plus error term plus u here as well. But now we use log. Instead of using original data, we use log. Transform variable log y and log x. Regress log y against log x, and then we have error term. Because we have error term here. So why we can interpret at the slope beta 1 as percent? So you see that's one. So if you just like this one, the difference between two values y2 and y1. So this one difference between two values log y2 and log y1 per unit change in the difference between log x2 and log x1. So this one, the difference between two log is actually give us approximate value of relative change. Okay. So if you open another file, this one the Excel file of fee. So it is when you use log information, it gives us approximate estimate of relative change. It's not exactly okay, but approximately similar or similar or equal number. Similar, it's not equal. So you see that let's say we have data. This one the same data that we just now. Cup the consumption and then price. So this is change in y. You take the difference between two. So this one, the difference between y two values of y. So y this one minus the previous one. So difference between two lah. Okay. And then if you divide, so this one the current value minus previous value divide by the previous one, it gives us what we call as a relative change. Okay, relative change. And then you multiply by 100, you get percent. Okay, you get percent. Now, if let's say you transform the variables using log transformation, now you use log y. This one you use this is the y. This calculated using the original value of y. But now you use log y. You transform using log transformation, log y, and you take the difference between two logs y, then you get this value, and this one is similar to the relative change in y. So this one, similar change in between two value of y is quite similar to the value if you calculate the relative change in y. Okay, relative change, the current value of y minus previous one over the previous one give you relative. You multiply 100, give you percent change between two value of y. Alright. So if you use log transformation, you take the difference between two log without divide by the previous value. You just take the difference only, and then you get similar value of estimate. So meaning that the difference between two value of y is approximately equal to relative change between two value of y. Okay, it's not exactly, but just approximate lah. Approximate. Okay, and if you multiply 100, then you get percent similar to the percent change. Okay, so that when you use log transformation, then you are able to interpret it. You can be able to interpret it as percent. So this one between y and x, but this one you use log transformation. So I mentioned before, the difference between two values of log two values of log y is approximately equal to relative change. Okay, relative change y2 minus y1 divided by y1. This the difference between two values of log is approximately equal to relative change between two values of y. So if you multiply 100, then it's percent. Percent change in y. And then this one as well, for the case of x2 also the same. Okay, this use a linear model between two value of x. This one between two value of log x. So this one between two value of log x is approximately equal to relative change in x. In between x, you multiply 100, then you get percent. Okay, so this one, if you multiply 100, then you can interpret in terms of percent. You can say that when x increase 1%, then y will increase by beta 1%. So this one doesn't matter if you multiply by 100 each, or you do not multiply, it's just the same value, because if you multiply, then this one cancel out this one, then it's just the same estimate. Understand? So this one, if basically you want to have percent, because this one gives us relative change. the difference between two values gives us a relative change between y, two value of y, between y. You multiply 100, you get percent. But this one, because both numerator and denominator, in order to get electricity estimate percent, if you multiply or you not multiply, they're the same. Because if you multiply, then this one cancel out this one. They're the same. Okay. So you don't need to multiply. So later on, when we use semi-log model, then you have to multiply because later I will show you, I will explain to you. So for this one, for double log model, you do not need to multiply with 100 because whether you multiply or not, you just get the same because this one cancel out. This one. Yeah. So for the double log model, that's why you are able to use the estimated slope as estimate of elasticity because it is approximately equal to relative change, the difference between two logs. Okay. So the estimated price elasticity of demand is 0.25305. Even though the estimated coefficient of the slope is negative value, so meaning that when the price increase, the demand will reduce. So the price elasticity of demand is taken as positive value. Normally we say we just take the value itself. Okay. So for every 1% increase in price, quantity demanded will increase as much as. So this one you not mention as how many cups, you just mention percent. Okay. So when the price increase 1%, how many percent the demand will reduce or increase? So in this case, the demand reduced by 0.2531%. Okay. And then as the value of price elasticity, in absolute value is less than 1, so we can see that demand for coffee is not price elastic. So if when x increase 1%, y increase or decrease more than 1%, then we say if there is elastic to the so this one is not elastic because less than 1. So demand is elastic of price. Price elastic. Okay. And then semi-log model. Semi-log models are the adaptation of double log model whereby only a few variables are transformed by natural logarithm. Semi-log model can be in different form as follows. So we can have what we call as linear log model, so link log. So linear log model, when we use the original value of y, but we use log transform of x values. So this is linear log. Linear for the dependent, log for the independent. Okay, linear log or linear log. Or we also can have mixed model, so meaning that, so it's not, for example, in this case for the independent variable, we have x1 to be the original values and x2 we use the log transform values. And log linear model when dependent variable using log transform values and your independent variable all are original values. Okay, without log transformation. So if independent variables in theory linearly related to the left hand side of the equation y or log y, then the independent variable should enter the relation without log transformation, just like this one. Okay. If the theoretical relationship is not linear, then log transformation might be suitable. The first and second regression equation model is equation where the effects of x on y become smaller when x increase. So as an example, both equations can be used if y is consumption and x2 is income. When income increases, consumption increases by a small rate after income reaches a certain level. This effect is well represented in the relation which take log of x. So let's say you have your y is consumption. Y consumption, and then your X is income. So Y consumption, X income. And then if they see your data behave like this lah, something like this. This, but certain, when it reach certain value of income, then it start to have a smaller rate of increase, something like that lah. So instead of using a straight line to represent the relationship between Y and X, so you use straight line is not suitable lah, because you use straight line, then it produce something like, so it's not suitable. So it's better to use a line that properly capture the relationship. So in this case, for this kind of data, it's more suitable to use original value of Y, so meaning that linear and linear log model. So you have beta 1 log X, and then error term. So to have this kind of ratio between Y and X, then instead of using linear model, it's better to use linear log model. Yeah. So because in this case, for those, for example, for lower income people, they spend quite large portion of their income for consumption. But then for higher income people or population or certain segment of population, they spend less portion of their income for consumption, more for saving, for example. That's why you have something like this. Okay. Alright, so this effect is when income increases, consumption increases by a smaller rate after income reaches to a certain level. So the third model is commonly used to estimate economic growth of different countries or regions. Theory says that the economic growth is non-linear or is exponential form. The third model is one. The third model is useful to be used to estimate growth rate. Okay, let's say you have, later we have an example for this one. You want to say how many percent growth, okay, for the value of Y, given certain rate. Normally, if you want to estimate growth rate, then we use the dependent variable. Our independent variable is the time trend. So in the third equation, beta 1 and beta 2, third equation is one, beta 1 and beta 2, each represent the average percentage increase in the dependent variable on each one unit, not percent, increase in the corresponding independent variable. So this one, for this one, how to we interpret as when X increase 1 unit, Y will increase by percent. But you have to multiply by 100, later I show you. Because I mentioned before, the difference between 2 log Y gives us relative change. Okay, so in order to get percent, you have to multiply by 100. For double log model, it doesn't matter whether you multiply or not before. For double log model, it doesn't matter whether you multiply or not, you still get the same, because even if you multiply, this one cancel out, this one. Okay, but for this one, log linear, you have another, this one second. So this one log linear. Yeah. So how to interpret this one? So we have, you have the log transform value of dependent variable, but you use original value of X. So after you estimate, you get estimate of beta 1. So how to interpret the estimated value of beta 1? So we see that when S increase 1 unit, Y will increase by how many percent? Increase or decrease lah. If the value beta 1 positive, we say Y increase. If beta 1 negative, Y decrease. Okay, so when increase 1 unit, y increase by how many percent? Why? Because you look at this one, because this one, the slope represent it changes the difference between two value of log of y. So which is this is equivalent to relative change, right? This is the difference between two value of log y represent equivalent or approximately equal to relative change in y, and then this one is x, not log x. Our denominator is x. So x is not relative change. It's an absolute change between x. It's not relative change but absolute change. Okay. So in order to interpret a percent, then you have to multiply this one by 100. Yeah. So later we have an example. So you have to when you interpret, you have to be careful how to interpret correctly. Whether you have to multiply, you need to multiply 100 or not. Okay. So that's how we interpret this one. So as given here, you interpret this beta 1. The slope parameter represents percentage change in y per unit change in x. But in order to use that interpretation, you have to multiply the estimated value with 100. Okay. So in this one, in the third equation, beta 1, beta 2 each represent the average percentage increase in the dependent variable on each one unit, not percent, but x in unit, y in percent. Okay, increase in the corresponding independent variable. Log transformation for 0 is not defined. W variable and other variable that takes 0 values must be used without log transformation. So if you have W variable in model, W variable we have discussed, W variable the variable that we create to represent qualitative effects. Let's say gender, male and female. So you can create W variable to represent male, for example. So you have data, survey data, for example. Then male you put 1, female 0. That's W variable. Okay, 1 or 0, 1 or 0. 1 if that the event is present, 0 if not. Okay, so do not apply log, do not log on the variable because log on 0, I mean you cannot. Okay, because so you cannot log 0, you cannot get values. So if the theory requires a dummy variable to have log information, make sure that dummy are defined by not taking 0 values. Normally we do not apply log on the dummy variable. Okay, so I'm not really able to think what situation that requires to apply log on dummy. But normally when we have dummy, we do not apply log information on the dummy variable. Okay, so this is another way to calculate elasticity between variable alternative, but the use of double log gives us direct estimate without having us to do calculation. So as explained in double log model section, elasticity is the percentage change in a variable as a result of change in another variable. Estimated beta 1 in double log model estimate the average percentage change in y for 1% change in x1 with the other variable remain constant. So the elasticity E for y variable on and the variable x is defined by this. So elasticity represents percentage change in y per percentage per unit percent per 1% change in x. Okay. So as an example, elasticity E for quantity demanded on price is defined by this, for the case of demand. So mathematically, this one can be rewrite or the equation, the formula for this is given by this. So there is the change in y per changes in y per y, that's 100 to get percent, or this one relative change. Okay. The change between y x per x, this one relative change in x is done 100 each, and you get. So this is equal to this one. So which is this one is relative, this one the change in y per unit change in x is equivalent to slope in the linear model. Okay, so this one just like in the linear model, linear model, this one linear model. So change in y per change in x, change delta y delta x. Okay. So meaning that we alternative to the Lovelock model, you also can estimate elasticity using linear model, but you have to calculate because this is equal to this loops from linear model times x over y. Okay. So where delta did not change in y or x for linear model, the estimated slope is given by estimated coefficient beta 1, beta I. Okay, so beta, I mean, if you have more than one I, x, okay, you can have more than beta. So in order to obtain elasticity, we have to multiply the coefficient of slope with the ratio x over y, but which value of x and y are to be chosen. So if you use the Lovelock model, you don't have the problem. So but this one, you from the definition of elasticity, we have this formula, so you can get slope from the linear model, but you have to multiply x over y. But which x over y? Because we have our data, we have many combination of x and y. This one, so one x and y, the second x and y, the third x and y, and so on. Okay. So considering data set used for Lovelock model, there are 11 pairs of x and y. If you use all of them, then you will have 11 different estimates of elasticity. In practice, however, elasticity is computed at mean or average of x and y values. With this, we obtain the estimate of mean elasticity. So you take average, average of x and so average of. So just now we have this one data for Lovelock model. The first example was one. So this one. So you have y and x. Open as a group, and then you can get the descriptive statistic in the sample, so you get the average mean x and y. So you can explore later on. You can explore how open as group, and then you select statistic, descriptive statistic. In the sample, then you get average. So you get mean of x, mean of y. And you can use that to calculate your mean elasticity. Okay. So using these values, the estimated elasticity is 0.02191. You need the slope. Okay, the slope parameter from model. So the first model before we have equation 1. The first model linear model, this one. So you simply replace y against x. So you get negative 0.47. You just not log y on log x, but y on x. So you get this one, the slope. But you have to, if you want to calculate this using this one, then you have to multiply this with the x over y. Okay. So you get negative 0.1971. This value differs from the value obtained based on the Lovelock model, which is negative 0.2531 as we obtained earlier. So the two methodology give different estimate of elasticity because the elasticity based on Lovelock model remain the same, as it does not take into account the price of which it was estimated, whereas elasticity based on the definition depends on the particular mean value. So just two different way of estimating elasticity between x and y, between y and x, and between demand and price for this particular example. So it's easier to use, although Lovelock model, although it's not exactly give us percent, it's just approximately, because approximately equal to relative change, you multiply 100 is approximately equal to percentage. But it gives us direct estimate. So instead of using linear model, we have to calculate. And that's another problem. So which value of x and y? So it use average, then it is mean elasticity. And then growth rate. the use of log linear model. So as explained in the semi-log model section, the semi-log model are commonly used to estimate the economic growth. In fact, its application is not only limited in estimating economic growth, but also applicable in measuring growth rate of other economic variables. Suppose we would like to determine the growth rate of real GNP in the US for the given period. Let YT represent the value of real GNP at time t, and y0 is value of the initial value of the real GNP. So we have the data GNP, and so this one normally when we want to use a log linear model to estimate a growth rate, then our dependent variable we use time trend. Time trend is a sequence of value from 1 to 3 representing time. Okay, you have annual data, then 1 for the first year, 2 for the second year, 3 for the third year, and so on until the last one. So this is what we call time trend. Okay. So now we call the formula of compound interest. If you learned before, I think at the grade level, normally I think quite likely that you learned before. So what we call the compound interest formula. So you have A P1 plus R, and so A is the amount of your, let's say you invest certain amount of money, fund in any investment instrument, for example, and then your P is principal, initial value, and you are able to calculate, you know the interest rate every year, if the rate is just the same, and then you are able to use this formula to get what is the amount supposed to be after certain year, right? So let's say if you want to know what is the value of A after 10 years of investment, let's say your P is 100, and then your interest rate 10%, 0.1, and then for 10 years. So after 10 years, let's say every year you get 10% interest profit. Okay, so after 10 years, then at the end of 10 years, you should be able to get 200. It's just example. So if let's say you have you know the value of A, you know the value of P, principal, you know initial value, and you know the last value. This is the initial value, principal. This is the last one, right? The amount that you invest initially, principal. So if you know the first value and the last value after 10 years, then you are able to do the reverse calculation to estimate. And then this one 10 years, for example 10 years, then you are able to do a reverse estimate to get the interest, the growth. So interest just like the growth. So we still use the same idea here. So this one we convert a transform using, let's say you have the data representing the last value YT, and then your initial value principal P is your initial value Y0, and then you have R, the interest rate, and then the years, the T is how many years. So let's say you have a time series data representing, for example, this one like GNP or GDP for certain number of years, and then you are able to use the data. You can use what we call as average model, the one we call as log linear model, to get estimate of the growth rate. So basically you estimate this one, the growth rate. Okay, the R. However, the question is, so it's not direct form, so you have to linearize it first using this one, using log. To convert, you apply log so that this can be written like this. So we need to regress log of y against time trend. So this one gives us estimate for the slope. So this one gives us estimate for the intercept. So meaning that if you regress using log linear, log y regress against time trend, then you are able to get estimate of the growth rate, the R lah. Okay. So adding in the error get what we call so this one is mathematical model. Even the first lecture we discussed about mathematical model. This one after we add, we know that we won't get exactly the same value of this and this, the right hand side and the left hand side equation. So you will have error term. So we add error term because mathematical model. T represent the time trend. Suppose T equal to 1 for the first year, 1972. The first year, T equal to 1. And therefore T 20 for the last one. Okay, for the last 1991. The final model is known as semi-log model because some variable is in log form. Before we look at the regression output, let us examine the characteristic of the model. In this model, the slope beta 1 measures the constant rate or relative change in y for unit change in the regressors. So time trend in this case, the regressor is the time trend. So beta 1 represents the relative change in y per unit change in x. So you have to be careful again. So when you want to interpret, you use log linear model. So when you interpret estimated coefficient, you have to interpret like this. Relative change in y per unit change in x, not percent. So this one relative, you multiply 100, you get percent. Okay. So the estimated slope gives you relative, I mentioned before. So this one gives you relative. So in order to interpret as percent, you have to multiply 100. So the estimated value of this one, beta 1, it does not give you percent, but it gives you relative change. Similar to double log model before. This one also gives relative change, this one relative change, but doesn't matter whether you don't need to multiply, because even if you multiply each of the 100, just the same. You cancel each other. Okay, this one you cancel out this one. But for the case of log linear, this one gives you relative change, not percent. So in order to interpret it as percent, you have to multiply with 100. Okay. So if you multiply the relative change in y with 100, we will get the percentage change of growth rate in y for unit change in x. Such models are very useful in cases where x variable is in the form of time, as in our geometric model, the model describes constant percentage. So 100 times beta 1 growth rate if the value is positive or declining rate is negative in y. This is why this model is known as a growth model. So to estimate the model, you open the data GMP. So we have our data. This one GMP. So you produce graph, a time plot, for example, line. So you'll be able to see this one. So now we want to use regression or the model to estimate growth rate. So what is the average growth per year? So just like R, the interest, it grows how many percent it grows every year, the average. So you want to know. So we can use log linear model to estimate the value, but in order to estimate the value, we need to have a regress this against time trend. Okay, that can be done. Basically, you can create, but I think I just show you the easier way lah. No need to create the time trend first. The time trend you can create, you can just create variable like this lah. You can create variable 1, 2, 3, and so on. Okay, but in use you don't need to do that because you can directly estimate. You go to quick estimate equation. So this one log linear. So your GNP must transform using log. Space C, space your time trend. So you can just use this command to get time trend. So this one, add trend plus 1. So in plus 1 because if you only put trend, it start from 0. If you only put add trend, the series start from 0, but we want it to start from 1. 1, 2, 3, and so on. Okay, so you have to plus 1 there. Okay, so log of y, log GNP, okay, so you get this one, estimate. So this estimate of the slope gives us relative change in x, which is time, per unit change, relative change in y per unit change in x. Okay. So this one relative change is not percent. This one relative. This one relative change in y per unit change in x. In your beta 1, the estimated value is relative change. So in order to interpret a percent, you have to multiply 100. That value, 0.024 times 100, then you can interpret a percent. Okay. So, referring back to example of real GNP, we can write the fitted regression as this one. The integration of this model is as follows. During the given 20 years, the real GNP in the US grows at a rate of 2.469% per year. So why not 0.024? Because this one after we multiply 100, okay, percent, 2.469%. Taking the antilog of 8, the intercept. So this gives us, this is actually y0, give an estimate of y0, log y0. So this is estimate of log the intercept gives us estimate of log. So what is y0? Y0 initial value, just like principal. principal, it's like principal, the initial value or investment, for example. The first value, not it's not the value of for the first year, but at the beginning of first year. Okay, or at the end of 1971, the beginning of the initial values. So this is the end of 72, but the beginning at time of 1972. So the intercept gives us estimate of log y0, y0, y0. So to get y0 is I use anti-log exponent. Exponent of this gives you estimate of y0. So GNP, the initial value of GNP at beginning of 1972 is equal to 3023. Okay, exponent of this exponent. So this one gives us, if you refer to this step, this node, beta 1 gives us estimate of log 1 plus r. If you want to get the growth rate per r, you have to calculate. But if you calculate, you will see that the r is approximately equal to this one. So no need to calculate. You can just take this value as estimate for the r. If you calculate, for example, this one we get estimate. So beta 1, so log 1 plus r is our beta 1 in the model. So beta 1 gives us estimate for this. So 1 plus r equal to exponent. So r exponent minus 1. So from the estimate of our model, we get exponent 0.02469. Alright, 993 minus 1. So equal to 0.00069. So just like before, R represents the growth rate. So in this case, 10%, 0.1, 10% per year. So this one, you have to get so this one relative change, so you multiply 100. So this just gives a relative change, which is this is quite almost the same to the value of estimate. So instead of calculate this one, you can just take the estimated value and use that as a estimated growth rate. Okay, so instead of you calculate this one, because the value is very close already, then you just take this one. Instead of wasting time to calculate, and you can just take the value of coefficient and use that as estimate of growth rate. So the use of log model, double log model, semi log model will not give you the exact elasticity. For example, double log is not exact elasticity, but approximately estimate of elasticity. Okay, as well as this one. And then another model is the one that we call as linear log. Okay, so this one you have the other term, so I forgot to put this one beta 0, beta 1 log x. This one y, beta, the correct one. So this is y. So this is what we call linear log model. Okay, so that's the econs. How to interpret? So you can interpret as for linear model to interpret as how many unit change in y per rate change in x. Okay. Because this one, the numerator is between y, the absolute change, and your denominator is the relative change. Okay, so if let's say you are using a linear log model, then you have to do it again. This one you divide and not multiply. If you use linear log model, you replace y against log of x, and then you get estimate of slope beta 1 here, beta 1. Beta 1 represent, in terms of interpretation, you say that when x increase 1 unit per, it represent absolute change in y per relative change in x. So if you want to interpret, you want to say that when x equals 1%, then the estimated coefficient you must divide by 100. Now multiply, so the whole beta 1 must divide by 100. Okay. So for log linear you multiply, but for linear log model you have to divide by 100. So we have another example. Later on I leave it to you to go through the example given here to see how we interpret different form of model: linear model, double log model, and then we have log linear and linear log. So this one I leave it to you. I just an example, additional example for you to see how the example of interpreting different form of model. Yeah. So for the case of linear log model, I think it's given. This one is linear. This one is log, double log. This one is log linear. Linear log. This one linear log lah. Linear log. So linear log you have to divide by 100. When you interpret estimated coefficient, you divide by 100. Okay, the estimate divide by 1. So again, you have to if you understand this one, if you understand this, I mean you should be able to no need to memorize. So you can easily remember it if you understand this. Okay. So when you have log, it represents relative. And then in order to interpret as percent, you have to multiply 100. But whether you multiply or you divide, depends lah. So this one you do not need to multiply or divide because the above one cancel the below one. Okay. But for this one, you multiply because for the above one represent relative. Okay. But this one you divide because the below one represent relative. Okay. So to get percent, this is the one you have to multiply. So basically the whole thing you divide lah. So beta divide by 100. Okay. Alright. 30 minutes break. Please be here at or before 8 p.m. So we do exercise. Number of questions. Next session.